Hello, welcome to es346 Basic Thermodynamics. These are examples, and the topic is water properties and processes. I'm Rourke Peterson. Here's the first example problem we're going to go through. The problem says we have a piston cylinder device that contains 0.005 cubic meters of liquid water and 0.9 cubic meters of water vapor in equilibrium at 600 kilopascals. Heat is then transferred at constant pressure until the temperature reaches 200 degrees Celsius. So we have a process occurring here, an initial state and a final state. The four things we're asked to find is what is the initial temperature of the water? That's a property, an intensive property. The second one is to determine the total mass of water. That is also a property. That's an extensive property. Part C, we need to calculate the final volume. So we need to go through the process to a new state and then find a property, which is the final volume. And then part D, we want to show this process on a PV diagram relative to the saturation line. So let's go ahead and do the first part. The first part says, what is the initial temperature of the water? I'm given what the pressure is. Initially, it's 600 kilopascals. That's one intensive variable. And since I've got a mixture, temperature and pressure are not independent. They are dependent variables. So I know what the temperature is. It's the saturation temperature. T is equal to T sat at 600 kilopascals. So I can get that value from the property tables. So let's go to the property tables. And what I want to do is look up my saturation properties of water. So I'm going to scroll down here to the right table. And what we have here is saturated water as a function of pressure, the pressure table, table A sub 5. So if I go ahead and look down here, there's my 600 kilopascal line, and I can just read straight across and find out what my saturated temperature is. It's 158.83. So T is 158.8 degrees Celsius. There's the answer to part A. Part B, we're asked to determine the total mass of water, and we initially have some liquid and some vapor. So the total mass is going to be the sum of the liquid plus the sum of the vapor. I'll call that M sub F and M sub V. So I need to determine what M sub F is because I'm not given the mass, I'm actually given the volume. So I can go ahead and get the mass from the volume using the specific volume. So big V divided by little v. And so I can get this value, V sub F, also from the table, because that lists all those properties before. So let's go back to the property tables. And so here's my 600 kilopascal line. If I look up here, V sub F is the third column down. So V sub F is 0.001101. So a pretty small value. We can go ahead and go back and put in our 0.005 cubic meters, divide that by the specific volume of 0.001101. The units of that are the meters cubed per kilogram. My meters cubed will cancel, and kilograms will come up into the numerator, and I have a value of 4.543 kilograms. So that's the mass of the liquid down here. Now I need to get the mass of the vapor. I'm going to do that the same way. M sub V is the volume of the vapor divided by, I'm going to call that M sub G to stick with the notation of the book. So M sub G is the total volume over the specific volume. That's 0.9 cubic meters. And V sub G, again, I'm going to get that from the property tables. Come back here. And V sub G, saturated vapor, is the fourth column. So looking over my fourth column, 0.3156. So 0.3156 meters cubed per kilogram. And that comes out to 2.852. So now we can go ahead and add that for what the total mass is. 4.543 plus 2.852, and the total mass is 7.395 kilograms. So there's the answer to part B. So now let's go down to part C, where it's asked to calculate what the final volume is. So I've now gone up through a process. So I need to figure out where am I now. Well, it happens at constant pressure. So I know that I'm still at 600 kilopascals. The problem says it's constant pressure. And then I'm also told the new condition, it's now 200 degrees Celsius. 200 degrees Celsius. And I started off at 158, so now I'm at 200. So now I've got pressure and temperature, but now I'm superheated. I'm above the saturation, so these are now two independent variables. And so I can go ahead and find out what my volume is at this new state. But in order to do that, I need to go to the superheated tables using these values. So let's do that. We're going to go back to our tables, and we're at saturation. See, 600, we boil at 158, but we went all the way up to 200. So that means that we're superheated. So now we need to go to the next table down, past the saturation to superheated. And our pressure is 600 kilopascals. So 600 kilopascals is 0.6 megapascals. So I'm using this table right here, and I'm at 300 degrees Celsius. And so I realize what my volume is at 600 kilopascals, and 200 degrees Celsius is 0.352. So 0.352. So V is 0.352. Units of that are meters cubed per kilogram. And now I'm going to call that little V2 because we're at a new state. And now I can find out what my new total volume is, multiplying that by the mass, which did not change, and V2. So my mass we got from part B, 7.395 kilograms, and then my specific volume of 0.352 meters cubed per kilogram. And my kilograms cancel, I get cubic meters, and my final volume is 2.604 meters cubed. So there's the answer to part C. So now in part D, it says show this process on a PV diagram relative to saturation. So I'll write down a PV relative to saturation. So there's my saturation curve. And now we think back, what was the initial conditions? Well, the initial conditions were we had a mixture, so we were somewhere underneath the saturation curve, perhaps right there, at a pressure of 600 kPa. And then we added heat, so we went across, became a saturated vapor, and then it kept going out here, all at a constant pressure. So there's 0.2. So there's 0.1, and that one right there is 0.2. So that goes ahead and completes this and tells us what it looks like on a PV diagram. Okay, here's the second example problem. This one's a little bit more complicated. Again, I have water, and it's initially at 200 kilopascals and 300 degrees Celsius. And it's contained in this piston cylinder device. But what's different here is I've got this little sets of stops, so it can kind of prevent it from getting to too small of a volume. The water is allowed to cool at constant pressure until it exists as a saturated vapor, and the pistons rest on the stops. So once it gets down to right there, I'm going to have a saturated vapor. Then the water continues to cool until the pressure is 100 kilopascals. So on a TV diagram relative to the saturation curve, we're going to go ahead and sketch this process, passing through initial, intermediate, and final states of the water. We'll go ahead and determine what the temperature, pressure, and specific volumes are for the all three states, and then we're going to go ahead on that process curve. We're going to find the overall change in internal energy, and we'll do that all on a per mass basis. All right, so let's go ahead and start off on this problem. So the first thing we want to do is think about what this looks like on a TV diagram. So it helps me to visualize this process. So here's TV, here's my saturation curve. And now water is initially at 200 kPa and 300 degrees Celsius. So what are my initial conditions? Are they superheated? Are they a mixture? Are they saturated? Well, we can figure that out. So we know at 200 kPa and 300 degrees Celsius. If we go to our property tables, and now we need to go back up. And so again, we're at 200 kPa. So if I look at 200 kPa, okay, so this is table A5, saturated water. 200 kPa, water would begin to boil at 120.21 degrees. But my problem is 300, so I'm much hotter than that. That means I'm superheated. So I know that the initial conditions in this problem are somewhere out there. That's 0.1. It's in the superheated region. Now when it's cooled, it's going to go ahead and decrease in volume. It does it at constant pressure, so I'm going to follow an isobar down until it becomes a saturated vapor, and that happens to be right when it hits the stops. And now we continue to cool, and so at that point we are going to be at a constant volume. We're going to come straight down, and so that right there is going to be my final point. So I'm going to go ahead and call this intermediate point, 0.2, and my final point, 0.3 right there. So this is an isobar. It's at 200 kPa. But once I hit the stops, the pressure is going to decrease. In fact, we're told that it decreases to 100 kPa. So there'd be another isobar there, which would be 100 kPa. And there's my final state. So that's what my process looks like. And that's pretty important to go ahead and keep track of what's going on here. So let's go ahead and look at what we've got. Here I've written up my initial conditions of pressure of 200 kPa, 300. We were given that the intermediate point was 200 kilopascals, and then my final pressure was 100. So I'm going to go ahead and sketch this up again here really quickly just to remind myself what it looks like. TV, we went here, and then straight down. Help me see my points 1, 2, and 3. So let's go ahead and determine what all of my properties are at all of these points. And so superheated region, pressure, and temperature, those are two independent variables. I can go ahead and figure out what the initial specific volume is from the superheated tables. So I'm going to go back to my superheated, and now we're at a pressure of 200 kilopascals. So 200 kilopascals is 0.2 megapascals, and I'm at a temperature of 300, so that tells me my volume is 1.316. So V is 1.316 cubic meters per kilogram. That's cubic meters. All right. So then 0.2. Let's look at where 0.2 is. We know the pressure is 200. The volume is decreased somewhat, and now we're at this point here. And so what we know is we have a saturated vapor. We could write that as X2 is equal to 1.0. The quality is exactly 1.0. And now if I wanted to determine things such as T2 and V2, because we're going to find all the properties, T2 is going to be the saturation temperature. So if I come back to my property tables, if I look at this line right up here in the top, it says saturation, and that is going to be this temperature here, 120.21. So the temperature is 120.21 degrees Celsius, and the volume, again, I can come back here, that's going to be saturation. So this line here that says sat is 120.21 for this table. It's 0.88578. So 0.88578 meters cubed per kilogram. All right. So let's go ahead and go to 0.3 down here. And what we know is, since it's a constant volume, or on a vertical line here, we know that V3 is equal to V2, which you just found at 0.88578. And then what is T3? Well, so T3, we're underneath the saturation curve here, so pressure and temperature are not independent. So 100 kilopascals, we want to go ahead and find out what is T-sat at 100 kPa. I'm going to come back, and now I got to go back up to my saturation properties. Actually, I took it back. We can actually kind of quickly do it here. So this is 0.1 megapascals or 100 kPa, and there's my T-sat value of 99.61. So I can actually pull it off of that table. So the value is 99.61 degrees Celsius. All right. So now I've got all those kinds of properties. The last part of the problem asked me to find out what the change in internal energy is. So there's going to be an energy associated with 0.1, and then an energy associated with 0.3. Energy left, so my energy went down, and let's find out what that change is. So the first thing is I want to find out what is U1, and U1, giving these conditions of pressure, temperature, volume, I was superheated, so I can find U1. Again, I'm going to do that, you guessed it, from the tables. This was at 200 kilopascals. And so U is the next column. It's the third column in this line right over here. And so I'm at 300 degrees Celsius. My value of U1 is 2808.8. So 2808.8, and the units that are kilojoules per kilogram. This whole problem was done per mass. All right, so now we're at point 3. We need to find the energy there, but now we've got a mixture. So we can't just simply look up the value of the internal energy, because it changes as I move across here between a liquid and a vapor. And so what I need to do is know how far across I am on this line, or in essence, I need to know what is my quality. So I need to determine what is X3, and X3 is going to be V minus VF over VG minus VF. I'm going to do all of that at point 3, so this is actually V3. And what is V3? Well, V3 was equal to V2. V2 was this value of 0.88578. And now I need the VF and VG values. I'm over here at 100 kilopascals, so now I need to go back to my tables. And now I need VF and VG. I can't actually do that on A6. I'm going to have to go back to A5 because that has all the V values that I need of both the liquid and the vapor. So here I am, saturated water pressure, 100 kilopascals, and so the two lines I want, here's VF, here is VG, so the third and fourth column of 100 kilopascals, and so I have 0.001 and then 1.694. So those are my value of VF and VG. So let's go ahead and put that on here. So this is minus 0.001, a pretty small value. It's actually pretty insignificant. And then 1.6491 minus 0.001. And now I can go ahead and get what my quality is. And my quality is 0.5223. Now, so you know this value just tells me what the mass of vapor is over the total mass. So now I need to go ahead and I can calculate U3. I'm going to use kind of rearrange this type of weighted equation here, where this is going to be UF plus X3 UFG. And so these values of UF and UFG, again, I'm going to get those for the tables, for the saturation tables. So come back here. I'm on the 100 kilopascal line. And so where's my UF value? So I'm going to look down here. UF at 100 is 417. And UFG, which is the difference between these two columns here, is 2088.2. So those are the ones that go into that equation. So UF is equal to 417.4 minus my quality that I just calculated of 0.5223, and UFG is 2088.2. And then if I do that arithmetic there, I get 1508. That is kilojoules per kilogram. So there's the energy at the final state. It asked me what was delta U, the change in energy. So delta U, which would end up being equal to U1 minus U3. And so U1 was 2808.8 minus the value just calculated here, which was 1508. And that tells me it's about 1300 kilojoules per kilogram. So there's the change in energy from 1 to 0.3.